If you are all hearing me clearly, I want you to confirm if you're hearing me. Can you all confirm if you're hearing me clearly?
Yes.
Okay. Yeah, thank you so much. So I want to welcome everyone to my lecture today. Of course, today we mark the second week of the lecture. And of course, I'm going to share my screen right now. I'm going to share my screen. Okay, so if you are seeing my screen right now, I need you to confirm if you are actually seeing my screen now. Can everybody confirm that?
Yeah.
Okay, so the topic for today is actually called decomposing the variation of y. Y is basically the response. But you know why? Before I go into today's topic, I would like to have a recap so that you can actually see connection between what we want to do today and what we've done before. Okay, I remember last week I introduced you to our linear regression model. Okay, looking at linear regression model, we basically want to characterize a relationship between two variables, okay, in such a way that we basically want to have a way of, predicting one variable from the other one. And of course, that is the essence of what we actually doing. So we want to study relationship between two variables, like I said. One is a predictor variable, and the other one is a response variable. And of course, using the relationship, if we're able to understand that, then we can make a prediction of one from the other. I remember I specify the linear regression model. From there, I walk you through how to estimate the parameters in linear regression model. Of course, on Friday, I actually walk you through how to fit simple linear regression model to data set, okay, using R software. And of course, I also remember in the lecture, I walk you through how you can actually, I walk you through the assumptions underlying the use of linear regression model. And of course, I actually told you that a model is as good as assumption putting into a model. Okay, so I also walk you through some basic fundamentals that has to do with the linear regression model. And of course, I remember I walk you through how we can actually, um, you know, uh, investigate whether assumption hold, like assumptions of linearity. I remember I walk you through, we generate a scatter plot. Well, that is what we did in the preliminary investigation. And I also walk you through how you can actually generate a residual plot and among some other things. But let me tell you, what is the purpose of today's lecture? The purpose of today's lecture is just like, okay, we have a response variable that we also call the outcome variable. And we basically want to decompose the variation around that, and so that we'll be able to measure, uh, you know, what is actually the amount of variation explained by the model, and we can also be able to figure out what the unexplained variation is going to be. So that is the purpose of today's lecture. And of course, basically, going to use an example from, using the NASA weight of male kangaroo, of a great kangaroos. Okay, if you take a look at this kangaroo right now, we actually want to study the NASA weight of that. And you know what? Study the NASA weight of that. What are we trying to do? We basically, because we know there's a kind of variations in the world. And that is the reason why we basically, what we want to do is we took a sample of 45 kangaroos. Okay, we took a random sample of 45 kangaroos. Why do we have to take 45? We actually have to take like a sample size of more than one because we basically want, on average, we want to say what is the the NASA weight of male kangaroos. Okay, so we actually from kangaroo number 1 to kangaroo number 45, we actually measure the NASA weight. I wanted to take a look at what I'm doing here. Okay, the Y1 represents the NASA weight of the first kangaroo. The Y2 represents the NASA weight of the second kangaroo, up to 45 kangaroos. And we added all of that together. Of course, if you want to find out what the average is, you're basically going to divide by the numbers of kangaroos. And that actually gives us 244.16. So 244.16 is actually the average, which we also call the center. Okay, that's what we call the center. So if you take a look at what I have here, okay, that is more or less like the variations in the NASA weight of 45 kangaroos. Okay, you can see the maximum, you can see the minimum, but this guy here is basically the center. Okay, this is basically the center. And let me tell you this, the NASA weight that we are studying right now is basically the response. Why? Okay, don't forget what we basically want to do. We want to decompose why, but we are focusing on the why now, which is the response variable. Okay, we got the mean of that. Now, the next thing we basically want to do, we actually want to see how much total variation exists in y. If you really want to do that, the 244.16 that you got, which is the center, we basically want to measure how much, why deviate from the center. I'm going to say that again. When you take female kangaroos, we have 45 of them. We're basically going to have different values in terms of NASA weight. Okay. And you know what? The average that we got right now, what we want to do by actually finding the amount of total variation that exists in that is basically to compare the average that we got from the respective observation. Don't forget, we got 45 observations, right? And now, what is the mathematical formula to do that? The mathematical formula to do that is actually this. I'm going to tell you what I'm doing right now. The Y1 is basically the NASA weight of the first kangaroo. Y2 is basically going to be the NASA weight. Look at the NASA weight that I'm talking about, a millimeter per 10. Take a look at that. Okay, so the Y1, the Y2 up to Y45, they basically represent the 45 values that we obtain after trying to measure the NASA weight of 45 kangaroos. So what are we trying to do now? If you really want to measure the total variation that exists in the response, because before we can actually decompose that, we need to, of course, figure out what is the total variation in the response before we can think of decomposing that. And that is exactly what we want to find now. So we are actually subtracting 244.16, which is actually the center, which is the mean of the 45 kangaroos, the mean NASA weight of that. Then I'm going to subtract the center now from each of the value, and I'm going to square each of the difference, and I'm going to add them up. Okay, so when you add them up, we're going to have 40,196. So 40,196 is basically the total variation that exists around response. Let me tell you, in statistical modeling, okay, what we normally, in statistical modeling, actually what we normally do is, particularly when we identify what the response is and what the predator is, there is, total variation, let's say total variation around the response, which we have been able to figure out now. This 40,196, if we want to talk about that in percentage, is basically what I call 100% variation the other time. Okay, the absolute value of that is actually, for this one now, it's 40,196. Okay, so that is a total variation around the response. And of course, if you take a look at this guy now, okay, if I want to write that in short form, this is actually the formula. The Y bar is basically the average that we got, which is 244.16. That we're actually subtracting from each of the respective observation, which is starting from the observation number 1 to number 45. So take a look at that. Okay, so the next thing that I actually want to do now is basically, we now, when you take a look at what we did here, we're really focusing on NASA weed, right? We're focusing on NASA weed. Okay, when you take a look at that, we are only focusing on NASA weed. We're focusing on this guy here. Okay, which means we're only looking at the response. Okay, but you know what? Let's assume that we have a good news now. And what is the good news? In addition to having the NASA weight, okay, of the 45 kangaroos, probably my colleagues actually collected the NASA length as well. Okay, initially we had the NASA weight, right? Which happens to be the response, but right now we have another variable that we call NASA length, and we're basically going to denote, or we're going to represent, symbolically, we're going to represent the NASA length with X, and we're going to represent the NASA weight with Y. And what do we want to see now? Okay, since we collected NASA weight from 45 kangaroos, and from the same kangaroos, we also collected the NASA length. Then we basically want to see if there's a relationship between them, so that we can actually use, information about predator to figure out the NASA weight. So take a look at that now. So what am I doing right now? I think I'm actually generating a scatter plot. You remember the other time, if you are looking for relationship between two variables, one part of the preliminary investigation is basically to conduct a scatter plot. And of course, the scatter plot I'm showing now is basically the diagrammatical plotting of the response against the predator variable. Take a look at that now. So, and that is what you can see. So the weight is actually the response, and the length is actually the predator. Take a look at that. Okay, you know what I just indicated now? I tried to put the average that we got the other time, which is 244.16. And of course, you can see a straight line, right? I'm not talking about the horizontal line. The horizontal line is actually the mean, but the diagonal blue line is actually the line of best fit. Before I move on, can you all confirm again if you are all hearing me clearly? If you're all hearing me clearly, I need you to say yes, or you comment yes. Okay, thank you so much. And thank you for confirming that. Now, we actually want to obtain the regression model now that explains some variability in Y. Well, what is Y? The Y is actually the response variable. We basically want to measure the amount of variation out of the 40,196. That is the total variation in the response. We basically want to say how much of that, the model can explain. Now, the regression model that I'm actually using now, okay, we basically want to see, how much of that variation out of the response you can explain. Now, what is the formula to do that? What I'm trying to say now, if I know X, okay, can I know something about Y? What am I trying to say? If I know the NASA weight or NASA length, I'm going to say that again. If I know the NASA length of, kangaroo, of male kangaroo, can that actually tell me, can that give me information about the NASA weight of the same kangaroo? Don't forget, I'm actually using X to represent NASA length, and I'm using Y to represent NASA weight. Okay. So I also want to confirm again, if everyone is hearing me clearly. Is everyone hearing me clearly? Okay, I think it's only one person that is answering now. Is everyone is hearing me clearly? Okay, thank you so much for confirming that. Okay, so now because of that, if we basically going to fit a linear regression model, take a look at that, we're going to get a beta now, we're going to get a beta one. I've already walked you through that because getting that, we believe that if I know something about X, can I actually know something about Y? Okay, if I know X, can I know Y? Something about Y. And don't forget, in this case, my X is actually the NASA length and the Y is a NASA weight. Okay, I just wanted to take note of that. Okay, so what I'm going to do now, we actually need to obtain regression sum of square, which we call a variation of Y explained. I'm going to say the variation of response that is of Y explained is actually called regression sum of square. Regression sum of square. Okay? Regression sum of square. And you know what? We also call that, explained variation. Okay, we also call that explained variations. That is what we also call that. And what is the formula if I really want to figure that out? If I want to figure that out, you know what I'm going to do? I'll first plug in, each of the values of the NASA length in the fitted regression model. I'll be able to obtain the predicted value, right? Which is Y cap. And you know what? I'm basically going to be subtract. Of course, I'm going to have 45 predicted values of the NASA weight. And I'm basically going to be subtracting the mean from each of that. This is different from what we did the other time. I'm going to show you now. The other time, we were actually subtracting the mean, okay, from the original observation. Look at that, Y1, Y2, up to Y45. There's no cap. Okay, these are original observation, the actual values of the response where we were trying to get the total variation. But if you want to get the explained variation, of course, you needed the model. And of course, this is the model right now. Then you need to have a prediction. Okay, you're going to have 45 prediction because you have 45 different values of X. Then you're basically going to be subtracting the mean. Oh my God, at the end of the day, 31,227.9 is the total explained variation. Now take a look at that now. Total variation that we call total sum of squared is actually 40,196. But you know what? Explained variation is 31,227.9. Okay. Now, this is the explained variation now. Now, I've walked you through what the total variation is around the response. Now, you have the explained variation. And the next thing that we actually want to figure out is what we call the unexplained. Because I told you the other time, a model cannot explain all the variations in the response. And that is the reason why this guy here is not given the same value as the total variation. The total variation was 40,196, but the explained variation is actually less than that. That is what we expect, even if you are using most powerful model. Okay, because model, I told you the other time, statistical model can never give us an exact reality. We're trying to use that to capture reality, but you know what? It can't give us exact reality. And that actually explains the reason why the total variation can never give you the same as the explained variation. There's always going to be unexplained variation. Okay, now let us now look at the unexplained variation now. How are we going to calculate the unexplained variation now? The unexplained variation, you remember the other time that I said residual, right? Which is going to be the y original observation minus y cap. Okay, original observation minus y cap is what you're trying to see. Here, we're actually going to subtract them. We're going to square them. We're going to sum them. And that becomes residual sum of square. So we call that residual sum of squares. Okay, that we can call RSS. Okay, residual sum of square. So the residual sum of square is actually talking about the total square of the error. Take a look at that. Okay, that's what we mean by residual sum of square. Okay, now as you can see now, this guy now is basically the unexplained variation. Okay, unexplained variation. Okay, now if I actually want to relate this to the example that we're doing right now, I'm basically gonna say it is not every variation in the nasal width that nasal length of a kangaroo can explain. The unexplained part now, the unexplained variation, I mean, the variation that cannot be attributed, the one that cannot be explained by, the nasal length of a kangaroo is actually 8,968.1. That is exactly what we mean. Now, what have we just done now? Okay, so I said mathematically speaking, this is the formula. If you want to write this in short form, and the RSS is basically residual sum of square that I actually called the unexplained variation. Okay, now when you take a look at that now the topic today is decomposing the total variation into various components. Now, this is a formula for the total variation. Now, we basically have, for the total variation, we have 40,196, and that has been splitted now. If you take a look at what I have now, okay, so this guy is equal to that guy plus that. So which means the total variation around the response has actually been decomposed or splitted or broken down into explained variation and unexplained variation. Now take a look at that. This is basically what I call the decomposition of the response variable. Can you all confirm again if you are hearing me clearly? Is everybody say hearing me clearly?
Yeah.
Okay, so that is exactly what we mean. Thank you so much, and thank you for confirming that. So this is how. So if you take a look at this guy now, okay, you're basically gonna say every statistical model that we're actually using, okay, we have a way of breaking them into the explained variation and the unexplained variation. Let me tell you, no matter what we try, uh, even when you are using the best model, the one you call best model, the unexplained variation will always exist. The unexplained variation can never be zero, because situation where unexplained variation equal to zero, then you are trying to say the total variation in response is the same thing as explained variation, and that is actually telling you that you basically have perfect model. There's no perfect model anywhere in the world. Now, can you just give me 1 second? I just want to use the bathroom. Thank you so much. Okay, can you confirm again if you're hearing me clearly? Can you confirm if I say hearing me? Can everyone confirm if I say hearing me clearly? Okay, thank you so much, and thank you for confirming that. Now, I'm going to show you an example now. What's the statistical model? Now, this is what I'm trying to say. The sum of square total, we call these guys of square, sum of square total. Okay, take a look at that, sum of square total. And this is sum of square regression, sum of square, okay, sum of square regression. Okay, the sum of square total is actually total variation. The sum of square regression is explained variation. And this guy here is residual. Residual sum of squares. Okay, okay, residual sum of squares. So take a look at that. So this is the decomposition of the variability, the response that I actually talk about. But you know what? This is basically synonymous with this. You get an orange. Take a look at that. That's an orange, right? Okay. Now you get an orange because you basically want to have access to the liquid contents in the orange, right? Okay, you remember I told you the other time that if we really want to understand the world, if we really want to take a decision in this world, and we don't want to regret that, okay, we need to understand the world, and the way to understand the world we live in, okay, is basically we need to collect our data set, and we believe that information that we actually need, that the information that will translate into knowledge, okay, information that will translate into knowledge for us to be able to take correct decision is actually embedded in data set. Now, right now, I'm trying to tell you now, this is more or less our data set. Okay, this orange now is our data set, but you know what? The information that we need, that we translate into knowledge, is actually in this orange. And what is the orange now? The liquid content is what we want to drink. So what are we going to do? What we're basically going to do, oh my God, we actually extract the liquid content, which is the one that we want to drink, which is the one I'm actually going to call in the information now, which is the one I'm going to call the explained variation now. And you know what? The remaining part of that is basically go into trash. So what I'm trying to tell you now is this, the total variation in the response is more or less as the entire orange, and why the one we extract from the entire orange is actually the liquid content that we actually want to drink. And of course, the remaining part is basically going into a trash. Okay, so this is a typical scenario, so real life situation where you basically need information, and I told you the information is basically hidden or embedded in the data set, and something needs to be done to extract that information. And whenever you extract information from data set, there's always going to be loss of information, and the one that get lost, we want to try and minimize that, is the one that go into a trash, is the one that we call the variation of the response that is not explained by the model. If you get the explanation now, I need you to say yes, or you comment yes. If you get my explanation now about this, I need you to say yes, or you comment yes. If you get the information now, do you get the information now? Do you get what I just passed across now? Are you here? Is everyone hearing me? If you get the information now, I need you to say yes, or you comment yes, but if you don't understand, please ask question. Okay, thank you so much. Thank you so much. Like I said, you pay for this service and you deserve to be served better. If you really understand, if you don't understand at all, please ask me, ask question, and I'm ready to go, to go back and re-explain. Okay, thank you so much. Okay, so that is the way it is. Okay, now we're going to have, anytime we have a total variation in the response, we're basically going to have the degree of freedom. Okay, in case we want to conduct an inference, we need degree of freedom. Now, if you're talking about total variation in the response, where we've put into consideration the entire sample space, the data set, sample size, then we're basically the degree of freedom is going to be n-1. And of course, because we're dealing with a simple linear regression where we got two parameters, the beta naught and the beta 1, of course, that would be 2 minus 1. The degree of freedom is going to be 1. Now, the degree of freedom for error is n-2. And there's something I wanted to take note. If you add 1 to this guy here, so what is 1 plus n-2 is basically going to give you n-1. Okay, so when you add the 2 degree of freedom, the degree of freedom for the regression and the degree of freedom for the residual sum of square, when you add that together, it's basically going to give you the degree of freedom for the total.
What is the degree of freedom?
Okay, thank you so much. In statistical analysis, we basically want to have a kind of freedom on our sample size. When we go into population, we're taking sample, okay? And when we take a sample, okay, which is a sample size n, okay? And we realize that if we want to find the average, okay, we're going to add all the data set together, divide by the number of observation. But if when you get an average, we also need to get how reliable is the average. And that is the reason why we normally go for variance. And you know what? Where you are supposed to use if you're calculating your variance and you divide by n, that would be biased. And that is not a good result at all. Okay, so if we actually want to have unbiased result, because we basically want to have unbiased result, then we need the degree of freedom. So the degree of freedom is more or less like taking something away from the sample size. Like right now, we are actually taking 1 away from the sample size. So n-1 now represents the degree of freedom. Like exercising freedom on the sample size, and is trying to tell you to what degree of that freedom. It's just like So people in this country, they're going to claim that, oh, we got liberty. Oh, I got freedom. But you know what? There's a limit to freedom. Okay. There is a limit to freedom. So that is exactly what we are trying to say here. Does that make sense to you right now?
Yeah.
Okay. Now, what is the essence of decomposing response variable into explained variation and unexplained variation? Is because we basically want to find, coefficient of determination that I call R squared. Okay, because you know why? The R squared is the ratio of the explained variation to the total variation. I'm going to say that again. You remember the other time when I said one of a way to validate a linear regression model is to investigate how much variation in the response the model was able to explain. Of course, because of that, the coefficient of determination is just going to be the ratio of the explained variation. I'm going to say R squared explained, okay, explained variation, okay, to the total variation, okay, to the total variation. And mathematically, explained variation symbolically is SS regression, and the total variation is SS total, okay? Then I try to show you the other time here, okay? Look at that. This divided by that. That is what we call the R squared, okay? Explained variation divided by the total variation. That's exactly what we call that, okay? Which you can also represent that way. So take a look at that. So R squared, and another way you can get R squared when you square correlation. I know you've heard about correlation before. Correlation is when you're trying to investigate the nature of the relationship that exists between two variables. Okay, correlation is different from coefficient of determination. Correlation is just going to tell you, it's going to tell you the degree of positivity or the degree of negativity, okay, of the relationship between two variables. Okay, correlation is also going to tell you, the strength. It's also going to tell you the strength of the relationship. It's going to tell you whether it is weak, okay, or strong. Okay, and not only that, it's also going to tell you the direction, and the direction is just like, is it positive or negative? Okay, that is correlation for you. But what I'm trying to say right now is the coefficient of determination. The coefficient of determination is the square of correlation. That's another way to get determinant of, to get a coefficient of determination. Okay, what is the range? The range of that is going to be from 0 to 1. Now the question now is, when you run your linear regression, just like what I show you on Friday, when you fit a linear regression model, you're basically going to see the whole of this as an output, as R output. Now, where is the R squared? Oh my God, this is the R squared. Anytime you see multiple R squared, that's what it means. Okay, that is how you can extract R squared from the body of the outputs of that you got using R. Look at that. That is your R squared. Now, this R squared right now is 0.7769. If you really want to know, if you take a look at what I have here, this is the beta naught, the beta naught, the beta one, I walk you through this the other time. Okay, this is the length now, the standard error and the p-value. And if you take a look at this guy now, is the R squared. If you really want to know how significant is this model, if you really want to see how much percentage variation in the response the predictor can explain, what I'm trying to say now, how much percentage variation, okay, in the NASA weight of kangaroo that can be explained by the NASA length. Now, if I want to know that, I should come here and I'm going to multiply that guy by 100, and that is 77.69%. That is what it means. 77.69% out of how many? Out of 100%. That's exactly what we mean. Okay, so this is one of the way to validate simple linear regression model. Okay, now in the decomposition of the data, I think I've already walked you through that the other time, how you can basically decompose data. Okay, now give me 1 second. There's something I quickly want to check now. Okay, yep. I think I've already. I'm going to share my screen right now. Give me 1 second. Okay, now I've walked you through how to obtain the R squared and how you can actually extract that from the R output. Okay, I think I've walked you through that. Okay, so what I'm talking about now, also in the composition of response, of course, you're actually going to have the Senra. Okay, when you have the plot like this, you compute what I showed you the other time, that of the sum of square residual, the sum of square regression, and so on like that. So what I'm trying to show you here, what I want to show now, I basically want to go mathematical now. If you take a look at what I have right now, okay, the dotted line, okay, this guy here is actually this guy here, okay, is actually the center, right? Which is a 3.1. Okay, and of course this guy here is a line of best fit, and of course I've walked you through how you can manually compute the the sum of squared for regression and the sum of squared for error and stuff like that. But the next thing, give me 1 second. The next thing I'm basically gonna do now is to show you how to obtain. I just want to show you, if you take a look at this guy, when I was subtracting the Y bar from Y, you remember that was what I was trying to do when I basically want to compute the total variation. Okay, now when you take a look at the right hand side, if I only introduce a cap, look at that. If I have YI minus Y bar, and I say plus YI cap minus YI cap. So it's still the same thing as that, because this guy is going to cancel out. But you know what? What I want to do now, I basically want to use them. Look at that. So I'm going to say the Y cap here, okay, minus this, okay? And of course, the Y here minus this. That is exactly what I've done there. Look at that. That is exactly, what I want to explain now. I want to use a, theoretical approach now. The other time when I was decomposing response variable, I was actually using, data set, but right now I don't want to use data set. I want to show you the mathematical way of actually decomposing, the response into two different kind of variation. Take a look at that now. Okay, now that is exactly what I have. And you know what? This is for each observation now. Okay, I believe mathematically how I go from here to here. I only introduce this guy, and this guy I can still cancel out. Okay, now for all observation now, this is for each observation. For all observation, I'm actually going to square each of that. Then I'm going to sum that over the sample size. Okay, I'm going to sum that over the sample size. Okay, and when I sum that over the sample size, that is actually, if you take a look at what I have right now, this guy is this guy here, this guy is actually this guy, and this guy is actually this guy. Okay, now what I'm trying to do now, what I've done here is just summing them, squaring each of that and summing them. But before that, I just want to show you something now really quick. Okay, if I square this, I'm basically going to square the whole of that, right? Now, here, I want to use, if I have A plus B all squared in mathematics, What is that? We are now A, that's acting as A, and this guy is acting as B. Okay, you know, this guy is just going to be A squared plus B squared plus 2AB, right? If you look at the way we do that in mathematics, right? Now you're going to see now. So when you do the multiplication now, okay, that is what you have. Look at that. You're going to have this guy squared, and 2 times each of that. So what are we actually using? We're using the rule in mathematics where you have A plus B all squared, where you can say A squared plus B squared plus 2AB. That is exactly what we are applying here to be able to get this side here. Take a look at that. So we're going mathematical. So what I'm trying to show you now is basically how you can actually show how to decompose the response variable into 2 components mathematically. That is exactly what I'm trying to show you now. Oh, can you see confirm again if you're still hearing me clearly?
Yeah.
Okay, thank you so much. If there's anyone, because I know what we're doing now is mathematical, if there's anyone who want to ask question, please go ahead and ask a question. If you're not clear with what I'm explaining now. Now, does that mean everyone is good, right? Or does that mean everyone is good with this explanation now? I need you to ask question if you don't understand. If you are good with the explanation now, I need you to comment yes, or you say yes. If you're good with this explanation now, okay, thank you so much. Okay, now that I have that, then I'm going to sum that across. You know, here I'm going to sum that. That's how you introduce that. For this, I'm also going to sum that. That's how I introduce that. This, I'm going to sum that. That's how I introduce that. And this, I'm going to sum that. That's why I introduced that, because we basically want to know the sum of square of deviation across the sample size. And that is the reason why I introduced the summation sign. Okay, now that's exactly. Now, if you now take a look at this guy now, we need to analyze that, because mathematically speaking, that entity is going to be 0. Okay, and we have a way to show that. Because if you're able to show that this guy equal to 0, you know what we have succeeded in doing? It means we have already have a proof, which is this, which is decomposing the total variation around response into 2 different components, to the explained variation and the unexplained variation. But the task that needed to be done now is basically this guy here. We actually need to prove that is equal to 0. Okay. Now, like I said, we need to prove that that is equal to 0. And you know what? We are actually going to use a page to prove that that guy equal to 0. And how are we going to prove that? I needed to pay attention now. This is a theoretical side of this material, which I basically need you to pay attention now. Take a look at that. What we want to show now, we basically want to prove that that guy equal to 0. Okay, and this is how to start. Okay, you know, we are starting from this side. We want to prove that the whole thing equal to 0, right? Now, I wanted to pay attention to what I want to do now. Okay, I needed to pay attention to what I want to do now. Now, this guy now, okay, it's basically, I can rewrite it this way. You know, 2 is a constant, and 2 can just come outside the summation sign. We got this guy now. Okay, now, if you take a look at the y-cap, what is a y-cap? The y-cap is a simple linear regression model. You remember the other time, okay, the y-cap, okay, is basically the simple linear regression model, the beta naught cap plus beta 1 cap x. So anywhere I say the y cap right now, I'm actually going to put the beta naught cap plus beta 1 cap x. And that is exactly what you see here. Take a look at this now. This guy is being replaced by this guy minus y bar. And anywhere, what have we just done? We only substituted for the y cap. Okay. I just wanted to take note of that. The y cap equal to that. That's exactly what we did here. we plug in for y cap, which is a fitted regression model. We plug in the beta naught cap plus the beta 1 cap x. Take a look at that. Okay, now that you have this one now, okay, the next thing now, we basically want to simplify, okay? We want to simplify now, okay? And what are we going to do? If we basically want to simplify, take a look at the beta naught cap, okay? Let me show you this. If y cap equal beta naught cap plus beta 1 cap x, then I also want to tell you the beta naught cap, if you look at the formula that I gave you the other time, is actually y bar minus beta 1 cap, x bar. Okay, you got to take note of that, which is exactly what you have here. So anywhere I see, the beta naught cap, I'm actually going to plug that in. Okay, now take a look at this. You got a beta naught cap here. You got a beta naught cap here. Then we're going to plug in this guy, y bar minus, and that is exactly what we just did here. If you take a look at that. So we've already plugged that in. So we are here now, okay? We are here now, okay? We plug in this guy into where we have a beta naught cap and beta naught cap there, and that actually gives us what we have now. Okay, now, it's making mathematical sense because, why is making mathematical sense? It's basically making mathematical sense now because the y bar here can cancel that y bar, okay? And we're only going to have this guy minus this guy, or minus that. So I'm actually going to have this guy now. Look at that, because this guy and that guy cancel out, okay? They actually cancel out. Then I still have this guy, which is still here. Look at that. Okay, now we are here now. We are on the third line now. Okay, now the next thing we're going to do now, if you take a look at these two here, the beta 1 cap is common, right? You can bring it out. Okay, we can actually bring the beta cap out. If you bring that out, which is right here, beta 1 cap, take a look at that. Okay, when you bring that out, what are you going to be left with here? You're going to be left with x minus x bar. Look at that. Okay, when you are left with the x minus x bar, don't forget this entity here. This entity is what I still bring here. Look at that. The only thing I just did to move from here to here is just to factorize that guy. And that's exactly what we bring out. Okay, that's exactly what we bring out. Okay, now we are here now, right? We are here now, right? So we are here now, okay? We are finally here now. Okay, now the next thing we actually going to do, since we're here, take a look at that. The beta 1 cap is common. We can actually bring it out. Bringing it out, we can write that as that. Look at that. We still have the whole of orders entity, okay, unchanged. Look at that. Okay, now I'm going to say we are here now. Okay, we are on that now. Okay, if you take a look at what I basically have right now, moving from here, okay, all this guy is basically here, right? You can see that now, right? Okay, and here we have factorized, and this is what we have, okay? And after factorizing now, okay, we are left with this guy now, okay? And, since we are left with that guy now, okay, we can use this guy now to multiply this and this. Okay, when you use that to multiply that and that, I'm actually going to have this times that, which is this guy, and this multiplied by that, that's going to be squared. Look at that. Can you see the square now? Now, this is where we are now. Okay, now, the next thing that we actually are going to do, we are here now. Okay, what I'm going to do now, the whole of this guy is what we call sum of square products. The whole of this guy is what we call sum of SXX. So this guy is XXX. This guy is XXSXY. Take a look at that. And that is why I'm trying to write here, where I'm trying to say this guy represent the whole of that, and this guy represent the whole of that. Look at that. Now, we are here now, right? We are here now. You can decide to divide both sides, okay, by this ratio. Now, if you take a look at this guy, it's the same thing as this. Beta 1 is the same thing as xxy divided by xxx. If I plug that in here and here, I'm actually going to have, look at that. Do you see that? Then this, when you have that guy now, okay, you're basically going to see what is going to cancel out. So this one squared, that one squared, so that is going to cancel that. You only have this guy now. Okay, now we're actually here now. Okay, and now that we are there now, you basically so what we're actually going to see next is this and this. They are equal. When you subtract them, that gives 0. And that is how to show that that entity equal to 0. But you know what? In exam, you are not going to be asked to show this. It's just for information on how we can prove this mathematically. I'm not going to ask you to show this at all, but it's just for information. Okay, now the question now is, I've walked you through the decomposition of the response variable and how, when we say decomposition of response variable, what statistical device or what statistical tool can we use for that? We use what we call the analysis of variance. The analysis of variance will enable us to partition, to decompose variation around response into explained variation and unexplained variation. Recall, this is our variance. Okay, recall that, right? Okay, and the total sum of square of variation is actually that, the variation around y that I showed you the other time. And all this was actually studied by Fisher, Ronald, and Snedeko. Okay, which I'm trying to show you the picture now. Okay, but you know what? This actually will lead us to testing, to make use of the F distribution that can actually be used to test the significance of the overall parameters in the linear regression model. But you know what? I will quickly take you to what you need now. Okay, now we have a model. There's an output from linear regression model. You remember the other time, we use a t-test to test the significance of beta 1 and the beta naught using this p-value here. This is the beta naught, right? And this is the beta 1. If I want to test the significance of each of that, I make use of a t-test. I walked you through that last week. And if I want to look at the significance of the overall parameters in the model, I'm going to make use of the f-test. Without the decomposition of the response, there is no way we can actually conduct a f-test. I'm going to say this again. Without decomposing, the response or the total variation around the response, there is no way we'll be able to conduct the f-test. Okay, so that is what I'm trying to show you now. Okay, now the f-test that I talk about. Okay, last week I said you make use of this p-value, right? And this is the F statistic value, right? And I said, because the p-value is less than 0.05, you're basically going to reject the non-hypothesis and conclude that the model is adequate, or you say there's a significant linear relationship between the variables under investigation. Now, if I really want to walk you through that proper, okay, it means under the non-hypothesis, I'm trying to say the beta, the intercept model is fantastic. Okay, this is what I'm actually testing. When I'm using f-test, I want to test between intercept model and full model. Take a look at that. The intercept is more or less like why the response equal to beta naught. Why the full model is trying to, okay, relationship exists. I'm actually going to have this. Okay, take a look at that. This is like without predator, okay, which we call the intercept model. Okay, without predator, you're trying to say here, you're trying to say the beta 1 equal to 0. When your slope equal to 0, you have the intercept model. Okay, when your beta 1 is not equal to 0, and that is why mathematically speaking, this is the hypothesis. Okay, this beta 1 equal to 0 now. The beta 1 equal to 0 now is representing the intercept model, and beta 1 not equal to 0 is actually representing the full model. Take a look at that. Okay, and what do we need? Well, if we really want to test that, we're basically going to use the F test. And without having a decomposition of the variation around response, we cannot do that. Okay, I'm going to show you now if you really want to do this. Now, this is a test statistic. Remember the other time I told you we need a sum of square regression, right? And RSA, we need residual sum of square, which is unexplained variation. Okay, but that is mathematical formula to do that. But I'm going to show you something now. If you really want to do that in R, okay, I'm going to tell you where it is in R. You know what you're doing here. All this that you're doing, where this is hypothesis that you are testing. This is a test statistic. This is a p-value. I want to tell you now, okay, it's actually here. This is the F statistic now that you got. This is a p-value. R will automatically generate that for you. I'm going to say that again. I'm going to go back. This is the hypothesis for that. This is the test statistic value. This is the one that will give you the F here, the F value here, 149.7. I need you to do something. If you actually, if you put sum of square regression that you got the other time, and the residual sum of squared, and sample size -2, if you do that, if you compute that, you basically is going to give you this guy here, 149.7. Okay, now take a look at that. And this is a p-value. Okay, the p-value here, we enable you to, since the p-value here is less than 0.05 level of significance, you're basically going to reject this model and conclude that the full model is appropriate. We use F tests to actually test between not having any model at all, which is the intercept model, okay, against the full model. The full model is when you have the beta 0 plus beta 1x. Take a look at that. And without the decomposition of the response variable, we may not be able to do that. Okay, I just wanted to take note of that. Okay, now we're now going to have the Anova table. The Anova table is basically going to show you in R how you can get the decomposition. Now, I wanted to take a look at this. This is, if you take a look at this, this is a sum of square regression. This guy is the residual sum of square. You remember the other time? I'm going to take you back so that you can see when we calculated that manually. You're going to see now. Okay, here. You see that? This guy and this guy that we calculated manually before. If you want to use R, after fitting your model, I'm going to tell you the code. It's just going to be Anova into the model. I'm going to show you now. You're going to see that. You don't need to worry yourself about using formula. You can actually use R code. You're basically going to be fine. Now, this mode here, if for you to get this, you do mode equal LM. Okay, I'm talking about the code now. Okay, the width is the response. Then you are looking at that on the length. Okay, and your data equal to whatever they call that, and that will give you. So when you do the summary, okay, into the mode, of course you're basically going to have it. Now, if you now want to have access to the Anova result, then it's basically going to be Anova into MOD. It's going to be Anova into MOD. Anova into MOD will give you analysis of variance. So the analysis of variance table is where you're basically going to see the decomposition. So right now, what I'm trying to tell you now, this guy here is the explained variation that we call, sum of square regression. And this guy here is RSS that we call residual sum of square, which we call unexplained variation. And of course, when you add this to this, when you add that together, that will give you the total variation. And you know what? The same p-value, the p-value here is going to be here. Okay, take a look at that. You know, you will only go further to the ANOVA into that if you really want to talk about, if you want to know what is the explained variation and what is the, you know, the unexplained variation. That is why you need the ANOVA into mode. Otherwise, you can just simply have your p-value here, and this is the F statistic. Then you can take your decision regarding, you know, the hypothesis you are actually testing. Okay. Yeah, so that is the analysis of variance table that I just talked about, and how useful is F-test in simple linear regression. The F-test is will enable us to test between the intercept model and full model. Okay, and another name for that is just that we are trying to test whether there's a significant linear relationship between the two variables under investigation. Is there anyone who need clarification? I think this is a question time now. I needed to ask me a question on what we've done today, and I'm actually going to respond to that. If there is anyone who actually want to ask question right now, is there anyone?
Could you explain how to calculate the F value and what's the meaning for the F value?
Okay, you mean I should calculate how to calculate? Do you say F value?
Yeah.
Okay, the F value will enable the reason why, if you are referring to this guy now, 149.7, which is also here in the regression output. Give me 1 second. I'm going to show you in the regression output, which is also here. Okay, and this is the corresponding p-value. The essence of calculating that is because we basically want to test between this intercept model and a full model. Now, let me tell you what the intercept model means. The intercept model means, this guy actually means, if I want to explain NASA width, I don't need information about the length. But this guy here said, so this is trying to say the NASA width, we do not need information. We do not need information about NASA length, about the length of kangaroo. If I want to talk about the width, that is what the intercept model is talking about. But the full model is trying to say, if we have information about NASA length, then that can be used to explain something about NASA width. Does that make sense to you now? What we use F-test to actually test? Do you understand that now?
Yeah.
Okay, it's like you are actually testing between two models. You basically want to say, if I know the NASA width of kangaroo, okay, is there anything I need to know before I can actually, before I can actually determine the NASA width of kangaroo? So the intercept model is trying to tell you, you do not need information about the length of kangaroo before you can actually figure out the NASA width of the same kangaroo. But the alternative here, which is a full model, is trying to tell you we need information about about the NASA length to be able to figure out the NASA width. And before you can actually do that, this the full model is actually telling you there's a connection, there's a relationship, there's a significant relationship between the NASA width and NASA length. Because before you can actually predict a variable from another variable, they must have an established relationship. And that's exactly what we're trying to investigate using F-test. Does that make sense to you now?
Yeah.
Okay. Do you have any other question? Is there anyone who have any other question, I'm going to give like 5 minutes, even more than 5 minutes to entertain a lot of questions. Is there anyone who want to ask question? I'm going to ask again. Is there anyone? Like I said, do not hide your feelings. You pay for this service. You deserve to be served better. If you need explanation about anything at all that I've presented today, please tell me now. I want to hear from you. Is there anyone who need information? Who need clarification on what I've just explained today? Is there anyone? Okay, maybe I'm going to reframe the question. If you really understand what I've explained today, I need you to say yes, or you comment yes. I just want to know if you really understand. Okay, thank you. If you really understand, okay, so which means you all understand that, but like I said, do not hide your feelings. Do not hide your feelings. Okay, ask question. If you need clarification now, I need you to ask question. Okay, in the absence of question, I'm actually going to assume that everything is right. And I want to use this opportunity to appreciate everyone who have attended my lecture today. And I'm going to say this. I'm going to adopt a new style from tomorrow. Anytime I teach, I'm also going to walk you through the lab session immediately, so that there will be a connection between the theoretical aspects and the practical aspects. I'm still going to walk you through that. I'm still going to conduct lab section on Friday, but in addition to the lectures, every Monday to Thursday, I'm also going to walk you through the corresponding R aspects. Okay, so that it will be there's something will be able to flow. You get what I mean? Okay. In the absence of any question, I'm going to say I want to appreciate everyone who have attended my lecture today. I hope you enjoying that. And until tomorrow again, and I'm actually going to come your way. Make sure you stay safe and have a lovely day. Bye for now, everyone. Yeah, thank you too. Yep.